What's up, guys? It's day 13. It is day 13, stream number 12 to be exactly correct, and we are live on the interwebs again. How are you guys? Thank you for joining us, all of you regulars and some new names I see here as well. Cheers for joining. Now this evening, I'm going to keep things a little bit quicker. I'm going to try and get some sleep this evening. As opposed to the last few nights, I've been going to bed at like 5 AM. After the live stream, I still have lots of stuff I have to do. So I've got into this kind of cycle of like going to bed progressively later by accident and getting up later as a result. And so my day is slowly shifting into going to bed at 5 AM, getting up at 2 PM. And I want to try and get out of that a little bit because I don't see much daylight, which kind of sucks. So how's it going, everyone? Hi from South Louisiana. How's it going? Hi from Michigan. Hello from the UK, Tampa, Florida. Hello. So, gentlemen, for those of you that were with us last night and or may have seen these live stream from last night, towards the end of yesterday's live stream, we looked at some really interesting stuff regarding this B2 Audio Rage Series 2500. Now we did a simple repair. The repair was very simple. Just needed a new rectifier and new power supply FETs. Very, very simple repair. But the interesting thing about that was when we started diving into the drive circuit for the power supply section, and kind of like looking at different tweaks we can make to potentially improve the efficiency and the power output of this power supply section. Now, let me show you a very good comment that I actually got on my live stream yesterday from somebody that is obviously very well versed in electronic design. So most of you guys will know that about 4 or 5 years ago, I didn't have a single clue what a MOSFET was. I didn't know anything about electronics whatsoever. And so all of the information which I'm relaying to you is just stuff that I have picked up from trial and error and just kind of like working things out myself, and a bit from Perry's guide. But generally all this kind of stuff about the dead time and switching losses and stuff like that, that's just stuff that I've kind of figured out or read a little bit online about, or that's come from you guys. So my deep understanding, my base understanding is quite low, but my practical knowledge is quite usable, I think, and I'm quite quick to learn. But so when last night when we were looking into the dead time and why the dead time was set so low and why the gate resistors was set so high, so the core reason for those things being set as they were, the core reason that we had 270 ohm gate resistors and the core reason that we had 36% dead time was due to reduce electromagnetic radiation and noise from the amplifiers, power supply section while switching. That is a fact. Now the two things go hand in hand. The high value gate resistor will kind of prevent the MOSFET from switching so hard, and because we have such a high value gate resistor, we also, as a result of the gate resistor being so high, the MOSFET will turn on and off slower. And in order to prevent any overlap with the switching, we need to set the dead time, or they needed to set the dead time. They set the dead time low to 36% so that there was enough time for the MOSFETs to turn off and to come down to 0 volts fully before the next pulse was sent. So the dead time was higher. There was a larger portion of the time was spent dead on the driver to account for this kind of slower operation of the power supply MOSFETs. Now we installed 47 ohm gate resistors instead of 270 ohms, which obviously allowed them to switch on and off much faster. And as a result of that, we could increase the dead time a little bit to get a little bit more power potential from the power supply section to cater for that that lower value gate resistor. Yesterday, when we were looking at changing the dead time, we were looking. There was this is sort of the first time I've really looked into it in great detail when changing the dead time and looking at kind of wave overlaps and stuff like that. And there was we did a few things. We changed the dead time from 36% to all up to the maximum for this drive IC, which was 47.7. At which point the FETs were, I think, what we call hard switching. So yeah, the turn on and turn off time on the drains was like exactly in line. There wasn't really much of a gap or a slope between the push pulls. It was like that as opposed to like that, and there was quite an overlap on the gate compared to the drain wave, where the gate would turn on before the FET has come down to 0 volts on the drain. So a very knowledgeable guy commented on my video, and I just want to try and find where. Here we go. I'll just find where it is, and we can all read it here. Oh, for goodness sake, where is it? Here we go. Here it is. Okay, so I'm just going to give you my screen here so we can read this together. Zoom in a touch. So, this is from Marco. And he says, hello, there is a reason for long dead time and higher gate resistors value. In a non-regulated push-pull converter, which is what this is, using the proper value of dead time, you can make it work in 0 voltage switching, which I think was mentioned last night in the chat. Maximizing its efficiency, you need to check at the same time with 2 probes the gate to drain to tune it. At the correct setting, you should see the drain waveform going to 0 volts before the gate starts to rise. This is 0 volt switching. If you shorten the dead time, you lose 0 volt switching. Not a big problem at idle, but can be under high load. The FETs will have far more switching losses. The rail voltage is not tried, we know that. Don't mess with these things if you don't exactly know what you're doing. In my opinion, the circuit is fine. It just had a shorted rectifier that killed the FETs. Nice job indeed. Okay, so thank you very much, Marco, if you are watching, for that information. I thanked him there as well. And now this is interesting because this is what we kind of touched a little bit on yesterday. When I first was pulling around the dead time there, what I first did was as I was turning the potentiometer up, we were looking at the gate wave compared to the drain wave. When we first did that, I did comment on there being an overlap past a certain point, and that's when I noticed the current draw on the power supply start to rise up a little bit from its kind of idle that it was sitting at with a higher dead time. And I commented on that and I thought, okay, maybe that's the point then. Maybe that's the kind of perfect point where we need to kind of leave it. And that was at about 43-ish% duty cycle. And then we sort of went back and forth in the chat a little bit, and we were saying, oh no, maybe not, maybe it should just be you know, hard switching, maybe it should be at, try and get as close to 50% duty cycle, it won't really matter. But I think that from his comments, and very sensible comments as well, at the end of the day, with this amplifier, I'm not being paid, and I'm not qualified, and I'm not being paid to make you know, underlying changes to this base circuit design here. This is a repair. I am providing a repair service here, so I need to repair the amplifier back to original state. Now, changing the gate resistor values from 270 ohms to 46, I did change the MOSFETs because I've put slightly better ones in. They're ones that I have in stock here, and these work absolutely fine in this amplifier. I've tested that fully. But to make actual changes to the dead time, which fundamentally could change how the amplifier behaves, that is not something that I have been asked specifically to do, and that is not something that I would say that I am trained enough, or I have enough experience in to do that, and you know, be comfortable that that's going to work ongoing for the customer. For me to do that, I would need to have one of these amplifiers of my own, or that is sent to me specifically by the manufacturer for me to trial these changes, you know, to test them for a long period of time at high load, various different voltages, various different heats and scenarios, and that's not something that we have time or that I'm being paid to do with this amplifier. So what we are going to do though is, based on the knowledge that we have about 0 volt switching and just going by general feel of this, instead of putting a very high duty cycle like we were maybe considering doing with a low value resistor on the dead time set for the 3525, what we're going to do is I'm going to give you a demonstration of what that guy is talking about in the comments with the 0 volt switching on the scope screen here, so you can see how he's suggesting that we tune it, and I'm going to then explain how I'm going to leave it for the customer, and you know, it should be much better than it was, and very reliable as well, kept within the kind of original specifications with these new MOSFETs and the lower gate resistors. So with the higher gate resistors, I imagine that 36% dead time was probably, you know, that was actually the highest. I think that was the highest resistor value that this chip could do anyway, so we couldn't get any more dead time. We couldn't go any lower on the duty cycle. But I imagine that with the high value gate resistors, it was needed to be that low, otherwise it just didn't turn off quick enough and there was too much overlap. But now we've got low value gate resistors in. We don't care about electromagnetic or radio frequency noise coming from the amplifier, because that's not an issue. I am not, you know, checking for that. We've gone through all the tests and stuff, so we don't need to worry about that. We just want maximum performance from this amplifier. So here's a demonstration then of how I'm going to set this amplifier up now finally for the customer, and we're going to power it up. We're going to start off with the dead time down at where it was at factory. So let's power it up and let's have a quick look. Okay, so what we have here is on probe number 1, which is this one, we are probing the MOSFET gate. So this is the gate drive going into the MOSFET. Now, probe number 2 here, this is the drain. This is the output of the MOSFET. Now, if we take a look, what we are looking for is we are looking for no overlap between the drain coming down to 0 volts and the next pulse of the gate starting, which is this bit right here. So we can see here with a 36% duty cycle, we are way safe. In fact, maybe too safe. You know, this leaves some performance on the table, having it this low. When we draw current from the amplifier, there's more performance there to be had, because we're off for quite a considerable time before the next pulse from the drive circuit. Now, if we start to turn up the duty cycle, you can see there that we start to close the gap until we get to a point where the drain turns off. At the point where the gate turns, the next pulse is sent from the gate. And look at this. Look at the current draw. Now, if I go back down to 36%, the current draw is stable on 1.6 amps. As I get to that sweet spot there, at 0 volt switching, we drop down to 1.5 amps. It's like probably 1.58 or something like that. We're actually dropping in idle current, which is, I imagine, you know, that's kind of suggestive of a sweet spot. That's suggestive of very harmonious operation. Now, if we go beyond that, point, you can see now, actually the scope's a bit bright, isn't it? I'm going to try and get that so it's not so bright. If we go beyond that point, you can see that there's now an overlap. And I think that the little triangle that we see in between this is the switching losses. Like this is kind of going to be lost, and this isn't ideal. This is what we don't want to see. We don't want to see a triangle there in between where the MOSFET is not down at 0 and the next pulse is sent. As we go even higher, all the way up to 47.7%, we can see here that the current draw shoots up quite drastically, all the way up to 1.8, and it was over 2 amps actually earlier. So yeah, that's not ideal. I think that from what I understand now, and from what we've read in the comment from this gentleman who obviously knows a bit more about it than we do, we want to be about here. Now this might change with current draw. As we draw current from amplifier, this might change slightly. But I think that is a very safe place to be with the dead time. It is right on where the MOSFET is turning off fully down to 0 volts. The current draw is down at a bare minimum, the lowest that it's ever been at idle. And yes, we have the next pulse coming on right there. So if I turn the voltage up now from 10 volts, we just want to make sure that by going up in voltage, it doesn't change this at all. It changes it slightly. So you can see with a higher voltage, actually changes it slightly. So we need to back off a little further. We're going to go all the way up to 14.5. Let's back off a little further still. Because this is where the amplifier will be used the most, at sort of 14 volts with the alternator charging. So that's where the amplifier is going to be used most. These amplifiers do run up all the way up to 18.5 volts, but the percentage of customers that will be using it up there is quite low. So I think that for this guy who's not using it at 18.5 volts, he'll be using it at sort of 14.5, 14.6 volts alternator charge. I think that this is a good place to leave it here. And yeah, that's what we're going to do. We're going to leave it there. You can see that as we go back down to 10 volts, that kind of backs off a bit. But who plays their amp down to 10 volts? What we're looking for is optimum performance at around 12 volts, between 12 and 14. So 12 volts there, and if we go up to 14.7, we can see that's about perfect. So that's where we're going to leave it. Now, I've been obviously doing this with the trimming potentiometer, so what we need to do now is replace that with a fixed resistor, and I think that we are just going to be in luck that the resistive value across that for the dead time control is actually going to be very conveniently around about 270 ohms, which is the value of the gate resistors we removed from the amplifier originally. So we can just reuse one of those and put that in for the dead time control instead. So let's remove our probes, let's confirm the resistance on the dead time set resistor, which is just here. Oh, it's actually a little higher. Okay, so it's up at 300 and I thought it was going to be around 270, but we're actually up at 376 ohms. All right, no worries. So I think the best thing to do then in that case is to just pop this to one side, order a 370 ohm resistor. I think we can probably get one of those from RS Components next day delivery and fit that before popping the case back on. I think that's the best thing to do in this case. We could do something janky. We could series a 270 with a 100. We could do that, but that's not going to look so pretty in the case, and we want this to be ultimately reliable. So we're gonna buy the correct value resistor for this and leave it at that. But I thought it was worth just doing a little bit at the start of this live stream to carry on from what we were looking at yesterday, explain a little further after I've done a little bit more research, and let you know how we're gonna leave it. These screws away, put the back on, and unscrew this from my power supply, and we're going to move on to the next amplifier, gentlemen. They're so beautiful, these B2 amps, aren't they? So clean in the white here. Looks lovely. So let's put this away safely. Wait for our final dead time resistor to arrive, and then that one's finished. Okay, let's see if you guys have any comments on that. What happened with the Hertz? Got sorted. The issue was either my test bench, my workbench, it perhaps didn't like the grounding between my signal generator and the power supply. So it's either that, or it could also be that we switched from 074 HC on the op amps to 084 HC. So one of those things seemed to have sorted it on the second amplifier. We put these 084s in and ran it on a floating signal generator instead of the one that I have sharing the ground with the amplifier. And yeah, we ran it for 20 minutes at all sorts of different voltages and they didn't die. So one of those two things sorted it out. I've just got to do the same to the other one, but I thought that was kind of a boring stream because you know, we've been doing the Hertz. We did the Hertz for like 3 live streams already, so I thought we'd move on. And I thought we'd move on and take a look at this Cadence. I believe this is pretty old school, hey? Oh, that's pretty cool. So this is a nice little touch here. So, Cadence. Cadence. Now, this is apparently quite an old school amplifier. One of the cool things about this amplifier is actually, you see the markings on here. They're actually upside down to what you normally expect, which makes sense because when you're looking at this amplifier, when you're looking at like wiring it up, generally you are looking at it kind of upside down here. So the fact that we've got all of the writing, the logo here, Sweet Poison, all of the markings for the terminals, they're actually written upside down, which is a nice touch. You know, it's just a little attention to detail. The same goes for the settings side. We've got all the settings which are kind of upside down to what you would normally expect to see. So, why is this amplifier here in my workshop? We're going to take a look inside first, because I'm sure, actually we're not going to take a look inside yet, because the back isn't one of those ones where it screws off nice and easy. We've got to take the side panels off. So we're going to power it up first, and we're going to see why it's in my workshop. Does it power up? Does it have audio? If there is an issue, then we'll take it apart and diagnose further. What is the normal duty cycle? When the amplifier was brand new out the factory, it's 36%. Yes, we're getting festive. I have been trying to wear a different festive jumper every stream because it's STREAMMAS. It's Christmas live streaming, so I've been trying to kind of get into the festive spirit. I've got about six Christmas jumpers that I cycle through. There's one Christmas jumper that I'm saving for, like, you know, a very close to Christmas day, because it is a very Christmassy jumper. It's like I think it's got like a Father Christmas like beard on it. It's all red and it's got like some gold buttons on it, so you know, that's very intense Christmas jumperness. So we're going to wait until it's like closer to the 25th to bust that one out. Yes, it's so blue that the camera can't cope. This is such a blue amplifier. Like, I don't know if this camera perhaps does a better job of it. It's really freaking blue. Yeah, it is a really good color. It's almost like it's that deep of a color that, and it's actually that nice of a finish. It's that nice of a finish that, you know, you could expect to perhaps see this on a vehicle. You know, it's almost like vehicle paint. It's quite orange peely though. Like it's not that that kind of smooth like vehicle paint, but it's definitely got the right vibe. You know, if you were to polish it all down and stuff, you could probably get it looking like a, you know, proper car paint here. All right, cool. So we've got power, ground, and remote hooked up. Let's connect up our signal from our frequency generator. And this is a 4-channel amplifier. No, it's not. It's a 2-channel amplifier. Line in left and right. That makes things nice and simple. Little 2-channel. So we're going to see whether we got audio output on either of those channels. Let's give it 553 hertz to start with. Let's get the gains and everything turned down. Input levels down nice and low already. There we go. Input level 10 volts. Well, that's actually freaking crazy high. Might need to actually bang that up a little bit to about 5. Shockwave. What the hell is shockwave? Got a knob here called shockwave. That must be some kind of janky bass boost. Crossover mode, 2-way or 3-way. Leave that on 2-way for now. High pass multiplier. We're going to keep that down at ×1. High pass crossover frequency. Okay, so we got a fixed high pass. By the looks of it, at 30 hertz, and low pass out ×1. The low pass goes all the way down to 30 as well. That's strange. Now this low pass knob does actually turn forever. The stopper has gone on the potentiometer, so it could need a new potentiometer there. Actually, it feels a bit janky going round. Actually, it feels like very click click click. I don't like how that feels. So that might need replacing. That could be one of the issues here. And we've got low pass, high pass, or full range. Oh, okay, that makes sense. So it's not a fixed high pass. If we select high pass, then the minimum is 30 hertz. So we can use that like a subsonic filter, but it's a bit high for a subsonic, to be honest. I'd probably just leave it on low pass, but we're going to switch to full range for now. We have separate controls for line out and amplifier, which is really nice to see as well. So you could use these crossover settings for not the amplifier itself, but you could use this crossover network to run another amplifier for tweeters, for example, which is a really nice touch. So you could use this amplifier for full range, you know, without the settings on the amplifier, and you could actually have a separate tweeter amplifier perhaps that you actually applied these settings to, which is pretty cool. Okay, cool. Let's fire up and see if we got audio on any of these outputs, any of these channels. So left and right over here. So we got the RCA plugged into left at the moment, which is over here. Oh, okay. Looks like we've got DC on the outputs here. So if I remove the RCA and power it up again, so on the left output, I'm going to turn the current down quite a bit there. Yeah, you see we've got like rail voltage on the left speaker terminal, and let's see if it's on the right one as well. Okay, no, so it's only on the left one. So that then tells us that we have most likely shorted left channel output transistors. So we need to take her apart then to have a look inside. You be very careful with the screwdriver here. I don't want to slip and scratch this paint. This amplifier is in goddamn near mint condition, so you need to be very careful with this one. If it were green, I would die, says Sniper. Do you like green stuff then, my friend? Is green your colour, or is green your least favourite colour? Would you die of disgust? It actually has a clip LED as well, which is really nice. This is a lovely little amplifier, guys. Has a little clip LED. You don't normally see that from these like kind of class AB 2 channels. Really nice. Okay, there we go. Side panel is off. Let's place that carefully over here. Now we should be able to slide this out. Now, I got a feeling this is going to take some convincing. I've got to, because this is all painted, and this obviously isn't going to have been moved in many years. So I think this is going to take some pretty hard convincing. What we might have to do, oh wait, here we go, just need to give it a bit of a wiggle. That side's come a bit loose. I think what we might have to do is actually go and grab a tool that arrived in the post today. Yesterday on the live stream, we had a gentleman called Reese Carney. He's actually a good friend of mine. I consider him a pretty good friend. I've done lots of work for him in the past, amplifier repair stuff. He noticed that yesterday on the live stream we were using a hammer to hammer the MOSFET clips back on, but at some point in the past I had needed like a soft tipped hammer, so I had duct taped like a piece of soft cloth or something to the front of the duct tape, and he noticed the duct tape on my hammer, and he just went on Amazon and ordered me a plastic soft hammer for things like this, where we might need to use some light impacting over it on this side to loosen this away from the because obviously this paint will have stuck this in here, and so it's come free on this side but not on the other side. So that is actually the perfect time to use the thing that arrived in the post this morning. So thank you very much, Reese. I'm just gonna, it's in the kitchen, it's just here. I'm gonna go grab that and we'll put it to use. Here we go then. Thank you very much, Reese Carney. Very, very, very handy. So we just want to give it some real light taps over. Look at this bad boy. Thorex plastic hammer. It's like a dinner bell. There we go. See, it's starting to slowly work its way out. So let's see if we can pull it from this point now. Nope, she's stuck in there, so we're probably just going to have to do some gentle hammering this evening to get this out. That noise must be so annoying, guys. Mute your audio for a bit, okay? Sorry. Okay, let's see if we've released it enough now. Okay, so it needs impact, and you can actually see why it needs impact, because the paint is so thick, alright? If we give you this camera, you can see here where it's sliding out. Can you see that line there? That is from obviously it kind of rubbing on the groove slot there, where it's so tight against it. So we do need to continue with the hammer to get this out, and in order to continue, I do need to take this side plate off because we're now flush with this, so I can't continue to hammer it any further. So we're gonna have to take this side plate off as well. No worries. Need to hit it back the other way to clean the paint out. Yes, true actually. We could do that. Let's try that just real quick. See if that works. Let's see if Scarol's idea works. So by hitting it back the other way, should kind of dislodge some of the paint that we have rubbed, which might make it easier to come out. Okay, now let's go back the other way again. I mean, that's definitely moving easier now than it was at the start. No, it's just too thick. It does need the hammer all the way, I think. Ba ba da ba bum. Lawrence says, setting gain with clip light should have speakers hooked up playing music. I usually listen to 40 Hz -10. Yeah, absolutely. Always have your speakers hooked up when setting gain, because having a load connected will cause your rail voltage to drop compared to having it unloaded. And obviously when your rail voltages drop, your clip point moves down. So you do need to have your load connected when setting your clip point when using a clip light. Do you know much about the home audio brand Cambridge Audio? I actually applied for a job at Cambridge Audio. I actually applied for a job in there. This was years ago, before I knew a great deal about electronics or anything. I still don't really know much about electronics, but before I knew anything at all, I applied for a job in amplifier. I think it was like either amplifier research and design or amplifier kind of testing, or something to do with amplifiers for Cambridge Audio. And I was hoping that with my enthusiasm and little knowledge that I did have, they would offer me a position where I'd get trained on the job and you know, be able to do stuff there. They said that they liked me, and they said they liked my enthusiasm and my love for audio, but they said that they were looking for someone with a bit more experience already with amplifier design and stuff like that. So I don't know if I'd get the job now. Maybe not. No, yeah, I got to check out their London headquarters. Got to check out all of the stuff they work on. The BMR speaker cone technology was pretty cool. Got to looking through their warehouse. They had like tons of home audio stuff from competitor brands that they were testing against their own. It was a really cool facility. Sam, what's your 9 to 5 job? It's this. This is what I do for a living. I repair car amplifiers. It's my 9 to 5 job, yes, but 9 PM to 5 AM, not 9 AM to 5 PM. There we go. Should be enough now, hopefully. There we go. Out she comes. Good stuff. So much paint on that, Jesus. Okay, wow. Very clean in here. Very clean in here. Look at this, gentlemen. Look at this. Let's get the big camera on you. So let's take a peek in here then. So here we have our power supply transformer. It's not seated down with any kind of silicone or adhesives, but my lord, this is incredibly, like, there are barely any loose leads. Okay, slightly loose on this red one here, but that is very, very solid considering that it's not actually fixed with any additional adhesive or anything like that. Pretty cool. Nice. Power supply filter capacitors. They leave a little bit. They leave a little bit to dream after, but not, you know, nothing too bad. We have a reverse polarity protection diode there, which is cool to see. That thing will hopefully save the amplifier if you hook it up backwards. Over here there is a 12 volts header, plus 12 volts maybe. Is that what it is? Revision H top. Not sure what that's for. That's potentially something 12 volts. You could hook up to that. Not too sure. Then over here, check this out. We have the power supply MOSFETs under these. Actually, here we go. So this is just the power supply FETs. We have what looks like what's that? 1, 2, 3, 4, 5, 6. 6 power supply FETs, 3 push, 3 pull. We have 10 ohm gate resistors, so very, very low gate resistors. Okay, pretty simple stuff. Where's the power supply drive circuit, actually, I wonder? Power supply drive circuit is all the way over here, I think. Let's have a quick look. What do we have on this PCB? We have a, yep, Kia 494. So that's the power supply PWM generation. We have a Kia 324F. That might be some kind of comparator doing protection circuit stuff. There's a bunch of components on here, actually. Pretty cool stuff. I imagine we've got the drive transistors maybe all the way over here, or they could actually be these big boys on the board here. We can check that with a multimeter, but we're not too bothered. The power supply is fine in this amplifier, so we're not going to do too much stuff with the power supply. But yeah, these guys could be the power supply drive transistors. I imagine they might be. Cool. Output section then. Let's take a look at the output section, which is over this side here. So this is class AB, so obviously we have the emitter resistors along here, nice low value emitter resistors. I will take these clamps off because we need to replace whatever's under here, transistors or MOSFETs. We don't know yet whether it's a MOSFET final or a regular BJT final class AB. Just in front of the drive circuit here, we will have our bias potentiometer. That is for setting the bias of the channel. So we've got one there and one for this channel over here. This is the drive circuit for the channel, for the class AB channel, which is on its own little driver board. Pretty cool. Rail capacitors. The brand of these rail capacitors is Nichicon. We also have, now this actually is interesting because you might take this apart initially and think, oh, this might be a class D, because we have an inductor here on the board. And if you see an inductor like this kind of size, often that is the filter inductor for the class D channel, the final filter inductor. But actually this is going to be a filter inductor for the rail voltages, to clean up the rail voltage even more. So what I said yesterday in last night's live stream is that the quality of the rail voltages, like the smoothness of the rail voltages and the lack of noise on the rail voltages for a class AB amplifier, is way more important than that in a class D amplifier. So yes, we have an inductor here to just sort of clean up the rail voltages after they've been rectified from the rectifiers on the board just down here. FEN16, sorry, FEN16, made in the USA. Look at that. What's better, an amp clipping detector or the DD1? Amp clipping detector is always the way that you should go. Amp clipping detector is the most accurate way of determining when your amplifier has reached clipping point. It's more accurate than any external tool, perhaps other than, weirdly enough actually, perhaps other than my my little tester, because my little tester, literally you can hear the sort of switching distortions when the rails touch the sine wave. So yeah, but I would go by the clipping light on the amplifier. Ooh, but the DD1 doesn't detect clipping. The DD1 detects distortion, which is different. So if you just want to know when your amp has reached clipping point, clipping light's fine. But if you want to look for distortions, then the DD1 does that. Like, the DD1 will tell you whether your wave is distorted or not, regardless of whether it's clipping. Whereas the clipping light will just tell you when it's clipping, not if any other issues in the system are causing the wave to distort. Max Powers, your voice is annoying. I imagine it probably is. Obviously over here in the UK, this kind of voice or accent is pretty normal. But depending on where you are in the world, if you guys are, if you're in the States, then a lot of the things I say will probably sound very strange. So yeah, I guess you could just mute it and turn on the subtitles, hey? Or just don't watch it, you know. All right, cool. So we figured out then that we have left channel. Left channel is shorted. Left channel has rail voltage on the speaker terminal. So let's determine which one is left channel first by using continuity. Taking the end of this here. Left channel is going to be the one closest to us, right about here. Left positive. So take our multimeter probe, whack it on left positive, and then see where we have continuity, which output we have continuity to. Okay, this one over here. So this is our left channel, and this is going to be the one that has probably shorted or damaged output transistors. So let's carefully remove the clips. Now, how am I going to get actually these ones? I should be able to get these off with a screwdriver down here. There we go, just lift that up ever so slightly, and then we can get underneath it and pry it off. Easy. There's one. Lift that up ever so slightly, just to allow our flathead to get underneath it, as we did the first one. There we go. Now our flathead should just about get underneath that. This one's a little tighter. I'm going to go for a smaller flathead to start with. Let's use the tweezers here. There we go. Okay, cool. So what outputs are these using? Let's have a look. I think that I've got a feeling this could be a MOSFET final class AB. We have, what do we have? Oh, now these are very difficult to get now. These are very difficult to get. BUZ21. BUZ21. I'm going to have to definitely do a little bit of looking up to remind myself what we can replace these with. Because these are very difficult. They're either very difficult to get or very expensive to get now. BUZ21. Now that just shows its age a little bit. These are pretty uncommon. You don't see these that often. And these are MOSFETs. So this is a MOSFET final class AB amplifier. Now let's see if any of these are shorted. I imagine they probably are, since we have DC on the speaker terminal. And they have these really annoying covers over the legs. So it's difficult to measure. So no continuity there. But we do have any continuity there? Nope, no continuity there. So that's that one. Let's just keep going. Check for continuity across these. Okay, so we have continuity then. No, we don't. That's that one. 1, 2, 3. Check the other bank. Okay, here we go. Here's our dead ones. So these three, these are going to be our dead bank probably. Yep, we have continuity there. 4 ohms. 60. What have we got? 58 ohms. And this one. This one at 58 ohms again. So the dead MOSFET, we've got a single one, a single dead MOSFET, which is this one right here. So for ease, for the minute, I'm just going to snap this bad boy off, because this is definitely dead. So let's snap this off, and we're going to see if the low resistance on the other ones goes away. Let's keep those leg covers, keep those safe for a moment. So we can confirm that this BUZ21 21 is dead. Yep, that's shorted right out. So the low resistance on the others should now have vanished. Yes, it has. We have normal looking readings from the others with that one removed. Now, with that MOSFET removed from the board, what I want to do is power it back up again and just make sure that we have audio on the left channel now. We should do. That will tell us whether our drive circuit has survived or whether our drive circuit has gone bad. I think actually these little headers in the board here, these might have been for when the amplifier was being worked on or tested. So in the factory, when this amplifier will have been tested, to keep unscrewing and screwing the wires into the terminals is quite time consuming. So I imagine they probably put these on here just to kind of speed up the the quality control process. Now I was hoping my bit of wire might fit in there, but I think it's a bit too thick. Yeah, it's a bit too thick, so we'll go in the normal way, shall we? DD1 also only detects one frequency. I thought you had a couple. I thought you could do DD1, I think you could do 40 Hertz and 1 kilohertz, is that right? My grandmother is from England and it's actually pleasant to hear your voice. Yeah, but you can't please everyone though, can you? Like, you know, can't please everyone. I don't mind that. There's going to be some people that don't like all kinds of stuff about one person. That's fine, that's cool. I'm just doing my thing. Is this half bridge? This is a this is a class AB, so I guess, yeah, half bridge, I guess. Yeah, it wouldn't be a full bridge class AB. You can bridge this amplifier. It's a bridgeable class AB amplifier, I think so. It's an Oldschool Cadence amp, probably half bridge class AB goodness. Yeah, it's a lovely little amplifier. This is a really lovely little amplifier. Gregory, how's it going? Yes, you caught me live. You did. Good job. Setting gains by ear is a no-no for me. I set them with an O-scope. Yep, listen for mechanical issues through the speakers. Yeah, absolutely. Good way to do it. Can you explain the difference between distortion and clipping? Because I thought they're the same thing. No, distortion is just any... Distortion is any change to the waveform shape that is not what you want. My words are bad. Any unintentional change to the shape of the waveform is distortion. I guess. Although that might not be exactly how it's defined, because obviously with a guitar amplifier you intentionally add distortion, or overdrive, which causes distortion, and that's intentional. Yeah, just the actual foundations of what distortion is and what classes distortion is I imagine very complex, and so you want to go ahead and read up some articles about what distortion exactly is, and you know how to define what is distortion and what isn't distortion. But yeah, it's any like when you're looking at a sine wave, a perfect pure sine wave, any variance from that perfect pure sine wave shape is distortion, whether it's a capping off at the top and bottom, which will be clipping, or whether there's harmonics on it from other things, or THD causing the waveform to change in shape slightly. So the waveform can change in shape slightly and be distortion but not be clipped, so it's not the same thing. So, are you live now? Yes, my friend, I'm live now. Reading your comments. Made in the USA, it's got to be from the 90s now. Well, it's in such good condition, it's very hard to tell. Usually, like, amplifiers that are this old, if it is made in the 90s, will be, you know, you'll be able to tell. Even if it's in good condition, you'll be able to tell still that, you know, there's something not quite right. You know, it's been used, or there'll be some scratches, or you know, there'll be some discoloration or something. You'll usually be able to tell a little bit. But this one looks fresh out the factory, so very difficult to tell exactly how this one is unless you know a lot about cadence and the amplifier models and stuff like that, which I don't. We don't really get a great deal of cadence over here, so. Okay, cool. So let's see if amplifier powers up now fully. Let's hope it does. And if it does, let's check whether we have audio on both channels, left and right. And the inputs are closest to the LEDs. Okay, well the output looks maybe quite noisy. There's quite a lot of noise on the outputs here, but it's also on the ground. So actually it could just be that it could just be that I need to ground the scope onto the output here instead to get an output reference. Because I imagine that the output section is floating. Yeah, that's much better. So now that I've grounded my scope to the amplifier's output section, now we have clean, clean stuff going on over here. Now let's take the RCA, plug it in, and it's the ones which are closest to the LEDs. Let's have a look, see if we have audio. Yep, so that is the right channel. Wow, that is really, really high voltage. This amplifier must actually put out some pretty decent power. Well, it's got a 35 amp fuse in it. So that would give a roughly, that would give about sort of 280 to 300 watts RMS in bridged, which is pretty cool. So yeah, per channel you'd be looking at about 150 watts per channel, which is pretty awesome. That's nice. We do have quite a lot of MOSFETs obviously in the output section, so that does make sense. MOSFET class AB amplifiers, you can get more power out of them than you can the transistor ones, BJT ones. Yep, and this is the channel that had the dead MOSFET in it. So easy repair. All we need to do then is the drive circuit was absolutely fine. We just had one single dead MOSFET. Nice easy repair on this nice old school amplifier. So all I need to do is either find I'm going to want to now, because obviously although the only one MOSFET died from this class AB, come on focus, we do want to replace ideally all 6 of these, especially in a MOSFET one. If it was BJTs, it wouldn't be such an issue using slightly different batch. BJTs in the output section of class AB amplifiers are not as fussy, but with them being MOSFETs, they are going to be a bit more fussy. So we are going to want to run the same batch across all 6 here for the A and B side of this output section. Now what's interesting as well is actually, look, take a look here. This amplifier has not been, I guess, assembled to its full potential. So this is the output section here. There's actually space for 2 additional MOSFETs. We've got one here, Q113 is left unused, and Q114 is left unused. So perhaps there was a step-up model from this amplifier that did a little more power, or perhaps ran down to a slightly lower impedance. The same on the other channel. We've got these couple of banks here, couple of there we go, couple of empty ones. It's the same by the looks of it on the power supply. Yeah, the power supply is the same. There's one MOSFET over here and one MOSFET location over here that is not used. Now adding one more MOSFET, or sorry, adding 2 more MOSFETs to each of the things, at the end of the day, I don't think is gonna yield crazy different results. So I wonder what the reason for that was. I wonder what the reason for having those trace pads there was. Was there another version of this amplifier that was you know, maybe slightly more powerful or different board or something like that. I also want to have a quick look at the filter knobs, because one of them was spinning freely and what didn't seem to be stopping. So let's have a quick look. Which one was that? We've got this one here, which is, that one seems fine. This one here, that one seems fine as well. This one here, that one seems okay. Okay, this one here, this one is pretty much freely spinning. So let's take a look and see if there's any issues we can spot with the potentiometers here. So we've got 4 potentiometers all paralleled together off of the same physical knob. So let's pop that back on now. Is it just that it spins in the plastic of the knob? That would be great if it does, because that means that we don't actually need to do anything with the potentiometers. Okay, yeah, it doesn't actually, they seem pretty stuck. I don't think that it's actually spinning the potentiometers. No, it's just spinning the knob. So the potentiometers aren't spinning. Now, are they just very, very tight? Do they need kind of a bit of isopropyl alcohol or contact cleaner? Let's take our pliers and try and spin this manually here. Let's go up ever so slightly here. Okay, so it does spin. It does spin with pliers, so that's fine. Maybe it's just a little bit tight for the plastic. I think it's also potentially missing. Is it supposed to have a stopper on the other side? No. What stops it from getting pushed through then? Nothing, I guess. Yeah, it's very, very stiff, and so as a result, it just kind of spins. It just kind of spins the plastic and doesn't actually turn the potentiometers. So let's grab some 99% isopropyl alcohol real quick, which is this bad boy right here. Let's see if we can clean up the wipers inside there. Smooth it out a little bit. Nope, still as stiff as it was before. Maybe we just have to replace these ones. What are these? These are 50k resistors. Because yeah, it's not turning the resistors at all. It's just turning the knob, but not actually the resistor. Just kind of wearing away this plastic. Or maybe actually what we can do is I can put some CA glue. Maybe I can put some CA glue in the knob, actually, in this bit here, so we can actually glue it in, which will give it the connection that it needs to drive these. I think that's probably what we'll do first. We'll just probably put some glue in there to get it glued to that shaft, so it's able to drive it. But yeah, so the amplifier is working fine. We just need to find replacement MOSFET for the BUZ21. I've got Subaru BRZ in my head. Let's take a look then. What are these BUZ21s? Oh, it looks like you can still buy these. I thought that these would be... Oh no, discontinued, okay. We want a data sheet somewhere. Is there a data sheet from RS? Here we go, data sheet. BUZ21. So it is a 100 volt MOSFET with a 21 amp drain current. Pulse drain current is 84. This is a very, very lightweight MOSFET. It should be nice and cheap, really. Or a replacement should be nice and cheap. How does the input capacitance... Oh, look at this baby. Look at this baby. Just 1,000. Just 1,000 to 1,300 picofarads of input capacitance. That is a baby. And the gate charge is probably going to be very, very small as well. We missed the gate charge. Where are we? Rise, tone, delay, output capacitance, transactance. The drain source on resistance is pretty darn high. That's fine. Where's the gate charge? Reverse recovery charge? Is that... No, that's not what it is. Maybe this one doesn't list gate charge. But, yeah. Okay, cool. Very, very baby MOSFET. I don't think that we can get these anymore. So we'll have to come up with a alternative. But I imagine if you go to eBay... I imagine that you'll find them on eBay, but they might not be legit. Look at this, loads of them from China. BUZ21. Now let's take a look. A legitimate BUZ21. Actually, where's it gone? Here it is. A legitimate BUZ21 should look something like this. So this one has the BUZ21, and then it has some markings on here. We have this logo here to the left hand side, this logo to the right hand side, which is going to be the batch number, and then we have, come on this camera, batch number on this side, logo on this side. We have an M stamped indent here, and then we also have gate drain source markings on the package. So that's what a legitimate one should look like. We also should have some indents on the side here on the metal. Got a little bit of an indentation there. And on the back, this is what the shape of the back plate should look like. So let's have a look at these ones on eBay. Yeah, that's definitely not legit. Guys, come on. You can almost see where they've rubbed that they've used acetone, or they've rubbed that down. You know, that is not real. Come on. How about these ones? Okay, these ones... No, I'm still not convinced about these ones. We have a stamp in the middle, but it's not the right marking. And the back of the MOSFET, again, doesn't have the right shape to it either. We don't have great gate drain source markings on it either. This looks potentially a little better, although we can't see the front of it. We can... Oh, no, we can. Oh, it's a very dark photo. So you can see there the indents at the back there. They're a slight different shape, but we do have the gate drain source marking. Just about make that out. We do have the correct M and the correct marking. So that one's probably going to be legit. But they are like, what's that, $5 each? So, you know, that gets pretty expensive when you're looking to buy 6 of them for this old school amplifier. So I think the best thing to do, obviously, in this case, is just to come up with an alternative. So if you're looking at alternative MOSFETs, RS Components is great. RS Components is great for finding alternatives because the filtering, the product filtering, it works fantastically on this website. So what we want to do is go to semiconductors, discrete semiconductors, which is here. Yep, and we'll go to MOSFETs. And then the first thing that I generally filter by first is pin count, because we know that we have 3 pins, so we can do that. And that then reduces the number, we then go mounting type, we're going for through hole. That then reduces the numbers of the amount of packages that we have to choose from. So then I go down and choose all of the ones which will be applicable here, TO220, TO220AB. The F, I think, is a closed back, which we don't particularly want. Let's choose that one. And then don't forget to scroll down and catch any of the ones which don't have the dash. So, for example, these ones just here. That's all our TO220 package style ones. Now we want to go for an N-channel FET, and we want to go for maximum drain source voltage was 100 volts. There's lots of options there. We could also go a little higher. You know, we can go anything higher than 100 is fine. But we want to try and keep the voltage low and the current low to keep the input capacitance and gate charge low, because that's what this circuit demands. So we want to hit, I think that's pretty much everything. Maximum continuous drain current. What was the originals there? I think the originals of this one was, I think it was like 20 something, was it? What was it? 21. So if we do a similar amount of drain current, then we should find that we have similar amounts of input capacitance and stuff. So we don't really want to go too much lower. So let's select 20, 22, 24, 26, 28. There we go. Let's check those. We've got 10 products in this selection. So let's see what it gives us. We have IRF 540. Now it's always a good sign if you see parts come up when you're looking at replacement parts. If you see parts come up in the list that you have seen before in similar amplifiers. So the IRF 540, in this case the 540 PBF, or also the IRF, we've got the N, or the N is more for switching. So in this case, the IRF 540 will probably make a great substitute because it is used in MOSFET final class AB amplifiers of this power and of this size. So yeah, it's used by other people, other manufacturers, so it's probably a good one to go for. Ones that you haven't seen before are probably less likely. So if you look at this, we've got IRF 540N. Now the N, actually this is a closed back, so we probably don't want to go for that anyway, because we want open back for the better heat dissipation. We've got STP 24NF10. Haven't seen these used in Class ABs before, but can't see why they wouldn't work, to be honest. The drain source resistance of the 540s is 77 milliohm, which is about the same as what the BUZ21s were. If we scroll down a bit further, the STP 24NF10s, they have a 70 milliohm. They probably work just fine as well. How much are they? They are 89p in a pack of 5, which is just one less than what we need. Whereas the 540s are a bit more expensive, so you know you can kind of you probably get away with going for the STPs just fine, and you wouldn't have any issues. Let's scroll down a bit further. We've got TK22A10. 22 amp, 100 volts there. They're nice and cheap, 77 pence in a pack of 6. That's handy. That's a handy package size if I ever saw one, seeing as we need 6. Wow, now that has a really low drain source resistance. That might actually indicate that the gate charge and gate capacitance is a little bit high. So this is back order anyway. So, but if these were in stock, let's have a quick look. Could we potentially use these? We have a drain current silicon limited. Okay, this is quite a bit higher actually. Power. I think the input capacitance. Actually, no. You know what? That's actually really low. I imagine that this part would work just fine as well if it was available. So yeah, that's probably going to be okay. That would probably work just fine, but it's not available, which is annoying because it's in a nice pack of 6. And then lastly, we have a closed back one there. Probably don't want to go for that one. We have an IRF 1310 NPBF. They only come in a pack of 50 on RS components, but we can check other websites which should sell them separately. How are we looking for this one then? We have half the on resistance, which should generate less heat from the amplifier, which is quite a good thing. But we don't want that to convert. We don't want that to translate into a higher input capacitance. No, it's pretty low still. So, you know, actually, if anything, I think that the ones to use here in this amplifier are either going to be the IRF i1310 NPBF, if I can find those on their own rather than a pack of 50, or just throw in some good old 540 PBFs that, you know, are used in many amplifiers of this type. Now, only one channel died, so we could leave the BUZs in the other channel, but we will give the customer the option in this case, seeing as we're replacing one channel with a new type of MOSFET, we could give them the option to just refresh both channels anyway while we have the amplifier apart in pieces. It wouldn't add a great deal to the repair cost. It might add another sort of 20 quid or like 15, 20 quid or something like that for the parts and the extra label replacing the other channel. So it's always good to give the customer that option to have all the MOSFETs matched on both channels. So yeah. Haha, use RFP 260s. I think the FP means full pack and is fully enclosed, no exposed metal tab. Yeah, actually, maybe. Yeah, full package, that would make sense. Bevids, I have been an electronics technician, field service engineer for 30 years now, and I'm thoroughly impressed that you have self-taught yourself to be an electronics technician. Thank you. I probably give off the impression that I know more than I do. I'm good at troubleshooting. I'm good at troubleshooting, and I pick up on kind of the way that things work quite quickly. The way that my brain works, I can figure out how things work and the kind of optimum environment that things want to work in quite quickly. But what I don't have is I don't have a underlying foundation of knowledge in electronics. So I only know what I know from fixing things and seeing how they work. So there are huge gaps in my knowledge for sure. But thanks. It's cool that you think that. Octoparts is great, but everything, all the results are American, American websites. So in the UK, I stick to RS Components, Farnell, Mercatio, and that's probably about it. Never order silicon from eBay. Absolutely, SnipeX is right. Guys, you might see SnipeX commenting in the live chat right here. This guy is 16 years old, and his knowledge is absolutely incredible for his age. So just bear that in mind. Awesome stuff. Awesome stuff. I'm still dumbfounded by that. At 16 years old, I was doing all kinds of nonsense with subwoofers in my bedroom and shit like that. Bevis, if you're able to get the same model of MOSFET, you should be able to just put it in without any problems. They work the same as BJTs. Wouldn't there be an issue though with VT? If the VT is different when used in parallel with each other, being MOSFETs, won't that cause one of them to turn on before the others? Because obviously when we're setting the bias, as we go up on the bias, if the VT of the new FET is lower, then that MOSFET will turn on before the other two in the parallel bank. Am I right or am I wrong in that case? Beverage Spanish doesn't matter if you don't know how to pronounce some technical terms in Spanish. Oh, dude, Mitchell, I missed that. Sorry, dude. Damn, thank you very much for the 20. Holy crap. Sam, why would just one of my new FETs get hot right away, but it powers on right now that I changed? They're not in protect, and then all the gates have square waves after I replace the gate resistors. So you're fitting brand new MOSFETs into a parallel bank on your amplifier. Is this power supply or output section? Let me know. And it works fine, but one MOSFET gets really hot. Is that right? Is that what you're saying? Usually, if one MOSFET is getting really hot, then either its tolerances, its specifications are way out compared to the others that it's in parallel with, or the gate resistor is bad, but you just said you replaced the gate resistor, so it probably isn't that. You would need to check the shape of the gate wave at the gate of the MOSFET while it's on and while it's getting hot to kind of see why. So let us know, Mitchell, what amplifier is it and what section, power supply or output. Frank says, so let me ask what kind of amplifier that you replaced that. This is a Cadence amplifier. Bevis, I responded to the DD1 question. DD1 picks up all frequencies and will tell you when distortion is introduced, just like a clip light on an amp. When you have one in your hands, try it. I have had DD1s in my hands plenty of times. They're great, but they don't work with all kinds of amplifiers. And I have seen, I don't understand why it would happen, but I've seen like amps blow up when connected to DD1s in the past. Could just be coincidence. They could just blown up because they were on their way out, but I don't know. I think it's overcomplicated. What Tony Damore has designed there is a very sophisticated detector of distortion in sine wave, which is great. But for people that just want to know when their amp is clipping, it doesn't need to be that complicated. My little speaker capacitor tweeter thing will tell you when your amp is clipping. It's very simple. Amps that come with a clip light, you don't need a DD1 because that tells you when it's clipping. But yeah, that's what 99.9% of people buying a DD1 are going to be using it for. So it's a little overcomplicated for that, probably. But it was ages ago. One of the first car amps you got after that 450 watt Fusion was a Vibe Monobox 4. Was that amp actually any good or nah? For its age, when the amplifier was produced, yeah, it was very good. What it was a HIP 4080 output based amplifier. Now the HIP 4080 was only really designed to run in amplifiers up to around about 800 watts RMS, or maybe sort of between 5 and 800 watts RMS. But designers pushed that chip further and further with output buffer transistors to get it to run more MOSFETs in parallel for more output power. So with the Vibe MB4, we saw there an amplifier that was doing about 1500 watts at 1 ohm using the 4080. It was a pretty well designed amplifier for its time based on that circuit. Yeah, not bad at all. Efficiency wasn't great, but it did make its rated power into 1 ohm, and yeah, it was pretty nice. Max Powers, I was just kidding. I don't mind anyway. Have you heard any systems with kick bass under the seat? Well, technically not under the seat. I have two systems with kick basses. I have my Vito, which has kick bass just behind the seat, the front seat, along the back of the wall, and I have my Proton, which has kick bass in the door card in the transmission line that fires into the footwell, which gives you like body impacting kick bass like from the door panels. Like, you know, you feel it in your chest, like when the real instruments like real life kind of double bass or boom boom, or like bass guitars and stuff like that, or like low tubas and stuff, they feel like they have real shape to them, and you know, you feel them like you were standing next to them. It's very cool. James says, hey man, could you put the amp info on the screen like you used to? Oh yes, yes, I'll start doing that again. I stopped doing that because I always forgot to update it. Servo subs are crazy, yes. Some blue LEDs inside, an acrylic cover. Yeah, I agree. This Cadence amp does look beautiful, doesn't it? It looks like, my camera won't really do it any justice because this is a really nasty Logitech camera from like 2002. But yes, it is lovely inside. Very nice design. Well, it's very neat, well laid out, not messy. Nice trace kind of pathways as well. I know it's silly, obviously they're just functional, but it looks really well assembled here. Made in the USA. Really, really nice amplifier. Let's zoom out of this camera and see if we can see it a little bit nicer on here. Yeah, it's so nice, and the blue PCB just really contrasts with the blue case. Like this kind of slightly lighter blue color where the traces actually run. It's so nice. Yeah, this is definitely an amp that you'd want to put a Perspex cover on or something for sure. By the way, have you found some friends to play VR with? No, I haven't. VR is freaking awesome. If anyone on the live chat right now is into VR, then let me know, because I really want some online friends to play VR games with. I'm so into VR, it's so sick. Like, I have the Pimax 5K Plus with the super wide field of view, and I can't stand anything else now, like trying the Vive or trying the Oculus. It just gives me like binoculars vision now that I'm used to the big wide field of vision of the Pimax. It's so good. Do you ever watch a YouTuber called Tech Moan? No, I haven't actually heard of him. Reese, I wonder if the Hertz would die when connected to one. Probably. Reese, did you see I used your present today in getting this amplifier open? Thank you very much for that, by the way, guys. Here we go. Reese Carney in the live chat bought me this hammer. It arrived from Amazon this morning. It smells so good. Like, you know, new shit smells great. Has a good new smell, this does. Thank you very much. It came in bloody handy with this amplifier getting it apart. Hi mate, what tool do you use for your video directing? I use OBS, Open Broadcast Software, which is this bad boy right here. It's very good, very simple, very easy to use. Alright gentlemen, I think we're going to lock the stream off here. I'm going to stick it to an hour and a half for this evening. I'm so tired, I'm going to bed so late. So I hope that you enjoyed. At the start of the live stream, if you just tuned in, we went over some of the things we were doing last night with the B2 audio dead time control. I explained how I'm going to be leaving that with the customer, and explained just a bit more about zero voltage, I can't remember what it's called now, zero voltage something. Yeah, brains fried, tired. But yeah, scroll back to the start of the live stream if you missed that. It's pretty interesting stuff. If you want to learn about dead time setting in a switching power supply, bit of information there. And a nice easy repair for me this evening on this Cadence 2-channel MOSFET final class AB, and a little bit of information about how to look for replacement MOSFETs if the ones that are in the amplifier are no longer available. Zero voltage switching, yes, that's the one. Zero. What did I say? Zero switching, voltage switching zero. Dude, DL, thanks for the 10, buddy. Thank you very much, man. That's awesome. Hi, Sam and chat. Can't stay, just pop in and say, hey, I'll have to watch the replay later. Spending time with the wifey. Yes, I need to do this. I need to spend some time with my partner as well in the evenings. Obviously been streaming a lot. So yeah, we're just gonna go and chill and maybe like crack on a film or something for a bit just now. Before, you know, whilst we go to sleep, so that would be nice. Cool, nice one, guys. I will see you tomorrow, probably a little bit earlier. Probably maybe I'm going to try and get on tomorrow. I'm going to try and start the live streams a bit earlier, so I'm going to try and go to bed earlier this evening so that I have more time in the day to do the things I need to do during the day. And then tomorrow we're probably going to get on the stream at around about 8:30 or 9 PM UK time, I think. So yeah, if you're interested, then jump on to your PC or your phone or your TV at that time, and I will see you then with some interesting amplifiers to look at. Thanks for tuning in, guys. Catch you tomorrow.